So my lecture is on determination of seismic base shear by equivalent static analysis as per IS 1893 2025 code. So in this session, I'm going to discuss about the introduction, equivalent static method. Under this equivalent static method, there are the parameters which we are going to discuss about earthquake zone factor, importance factor, design spectrum, site classes, approximate fundamental natural period, elastic force reduction factor, seismic weight, and design horizontal base shear, and how we distribute the base shear into each and every floor, that is the distribution of earthquake forces and the distribution of the vertical members. Then coming to the earthquake design philosophy. So what is the earthquake design philosophy? So before going to that, first, what is design philosophy? The design philosophy is defined as the fundamental safety concept that governs how a structure is expected to behave under loads. We have a structure, so on that structure various loads are acting. Now because of these loads, how safe we design the structure is, so that is what is the design philosophy. Now coming to the earthquake design philosophy, as we know that in IS 456 we have also design philosophy. Similar to that, in earthquake engineering, in earthquake code also we have a design philosophy. Now what is the design philosophy in earthquake code is, the first point is the we have a structure. For that structure, uh, under minor shaking, main members should not get damaged. What are the main members? The main members are the beams, columns. So these members should not get damaged under minor shaking. And buildings parts that do not carry load may sustain repairable damage. So you see the left side, you have a right side, you have a diagram which represents the building, minor shaking, moderate shaking, and strong shaking. And this picture is taken by Professor CVR Murthy. And you see the first diagram, you have a columns and you have a beams, and there is no failures in the columns and beams, but you can clearly observe there are cracks in the walls. So that could be a repairable damage, that is under minor shaking. Next, coming to the moderate shaking, under moderate shaking, main members may sustain a repairable damage. You can see there are some damages takes place in beams. Okay, and the third one is under strong shaking, main members may sustain severe damage, but building should not get collapse. Now you see there are damages in the columns and beams also, but it should not complete collapse of the building. So this is what is the design philosophy in the earthquake code. And as we know that as we continuously listening, waterproof. Okay, so our watch is a waterproof, but we cannot tell that water resistant. Okay, but what is the difference between resistance and proof in case of earthquake? Generally we heard that earthquake resistant structures, not earthquake proof structures. Now what is the difference between earthquake resistant and earthquake proof? Okay, so now we'll see the differences between earthquake resistant and earthquake proof. Now, the main objective or the main goal of earthquake resistant design means it prevents the catastrophic collapse of the building and allowing the people to evacuate safely. So that is what is the main objective of the earthquake resistant, the main goal of the earthquake resistant structure. Coming to the earthquake proof, it is zero damage, but zero damage, it is very very difficult in case of earthquake proof structures. But this zero damage aims to withstand any earthquake without any structural harm. Okay, and the philosophy of earthquake resistant design is it bends on it, it should not break. That is, the structure is allowed to take some damage in the form of energy dissipation or in the form of formation of plastic hinges, but the structure should not get collapsed. So that is what is the philosophy behind earthquake resistant design. But in case of earthquake proof, it eliminates all seismic effects, which is not possible. Okay, so whenever earthquake occurs, there should be some kind of damage takes place in the structure in reality. Okay. But without damage, it is very very difficult. a concept based on making the structure completely impersive to ground motions. It is very, very difficult. Now, what are the methods to resist the to construct the earthquake resistant structure is by providing the ductility. So these are the various methods by providing the ductility. And the second one is the damper, that is the energy absorbing devices. Okay, so viscous dampers, liquid dampers. So these kind of dampers may use uh, for earthquake resistant design of structures. And base isolation. So base isolation, there are two types of base isolations. One is active base isolation technique, and the other one is passive base isolation techniques. Okay, so using that one also we can reduce the displacement of the structure, so that we make the earthquake resistant. And steel reinforcement in concrete, so it increases the strength. So this comes under the concept of the code of IS 13920. So these are the methods to be used to make the structure earthquake resistant. But whereas in case of earthquake proof, the massive energy absorption is it is theoretically it is okay, but practically it is not possible. Okay, and highly advanced isolation techniques to be used to make the structure with zero damage. And the outcome of earthquake resistant structure is building is sacrificed for safety. But whereas in case of earthquake proof structures, the outcome is not practically achievable. So this is what is the main difference between earthquake resistant and earthquake proof structures. Next, what are the methods that are available in earthquake analysis? So the method of analysis shall be linear for the earthquake resistant design of structures, which can be performed by the following methods. So there are three methods that are available for earthquake analysis. One is static analysis, that is using by equivalent static method, and second one is the dynamic analysis. Under dynamic analysis, we have two approaches. One is a response spectrum method, the other one is response history method. So this response spectrum method and response history method, these two methods were already discussed in the day one session by Dr. Jay Prakash. Now we'll discuss about the static analysis by equivalent static method. So in this session, we'll discuss about the equivalent static method. So what is equivalent static method? Linear equivalent static method, a method of linear analysis of a structure to estimate the dynamic earthquake response considering the fundamental lateral mode of oscillation using the pseudo spectral acceleration response spectrum of the design earthquake hazard. So the same definition that I have taken from the clause 8.3.3 of AS 1893 2025 part 5. So for the sake of audience, or maybe for the sake of participants, I have given the clauses where I have taken the same maybe equations or maybe definitions. So the clause numbers and the IS 1893, either part 1 or part 5, it is clearly mentioned at the bottom of the slide. Next, applicability of the method. So this is also given in part 5 of IS 1893 table 9. If you refer clause 8.3.3.4, the applicability of the method. So for equivalent static method, earthquake zone, so in this case, we have to refer C 13.1, 15.1 and 17.1 of IS 1893 2025 part 5. And the I'll come to this earthquake zone part. And the second one is building category. So what are the various building category that we will discuss in the subsequent slides. And this equivalent static method is applicable for all building categories, and for similarly for all building configurations. But whereas a response spectrum method, which is a dynamic analysis, it is for a building, if it is located either zone 2, 3, 4, 5, 6, you have to perform response spectrum method. And for all building categories, and for building configurations recommended for irregular building, so for this case, we have to perform response spectrum method. But in the above case, that is the equivalent static method, the building configuration all means it is for a regular building or irregular building. For all the cases, you have to perform the equivalent static method. But here, this is recommended for irregular building. Irregular building, you have to consider the response spectrum method. But before going to that, first of all, we should understand what is regular building and what is irregular building. So regular building means where you don't have any re-entrant corners. Simply speaking, you take a rectangular plan of the building, or maybe a square. That kind of buildings are considered as a regular buildings. For irregular, the examples for irregular buildings, either plus shape buildings or maybe cross shaped buildings, L shaped buildings, those kind of buildings where you have re-entrant coordinates. So in the day one lecture on overview of IS 1893, Professor Pradeep Kumar Ramancharla was already discussed about the re-entrant coordinates, regular and irregular buildings. So for this kind of case, we have to perform the response spectrum method. And for a response history method, this is one of the methods in dynamic analysis. So if the building is located in Zone 2 to Zone 6, you have to perform the response history method. And for building categories, recommended for critical and special buildings, except for critical and special small buildings. So the definition which is given as per the section 13.1 and 15.1 and 17.1 is given here. So for small buildings, in a single story residential building with less than 50 meters square of built up area, 50 meters square of built up area with load bearing walls oriented along both principal plane directions to minimize the torsional irregularity, structural plant density not less than 15%, and laterally supported wall lengths not more than 3 meter. Structural analysis is not required in earthquake zones 2, 3 if masonry walls are provided with bands, and earthquake zones 4, 5 and 6 if masonry walls are provided with bands. So this is the clause which is given in section 13.1, 15.1 and 17.1 of part 5 of IS 1893. And response history method is applicable for building configuration. It is recommended for irregular building, similar to response spectrum method. Now here the building categories are critical building and special building. Now we will see what are the critical building and special building in the subsequent slides. Know what is the overall procedure for equivalent static method. So a step-by-step procedure is given in the diagram. So this diagram that I have taken from AI tool. Now you see here the first one. So when do we use this method? Okay, so this method is used, that is equivalent static method is used for structures where the first translation mode of oscillation governs the primary earthquake response. So this we will discuss in detail. And prepare the analytical model, that is you have to take the building and prepare the analytical model of the building and apply the gravity loads. So what are the gravity loads, dead loads, live loads, so floor finishes. So whatever the gravity loads that are there, you have to apply those gravity loads onto the structure and apply the earthquake load. So this is what we are going to discuss in this today's session. How do we perform the earthquake analysis to obtain the earthquake load, and how we distribute the earthquake loads on each and every floor and each and every frame, that we are going to discuss in the today's session. Then after that, the next step is combination of load effects. Okay, so you have to, there are various load combinations, so we have to consider the dead loads, live loads and earthquake loads. Basically the combination is 1.2 times of dead load, 1.2 times of live load, and earthquake load is a one type of combination that we have to perform. Like that, there are several load combinations which are given in the latest version of the code. And after that, after applying the load combinations onto the structure, then perform the analysis and extract the structural responses. So what are the structural responses? Either stresses, displacements. So those things we have to take, and after that you design the structure as per 13920. Okay, so this is what is the entire procedure for equivalent static method. Now we'll go to the step by in detail of how to calculate the earthquake loads. Okay, before going to that, first of all, we see what are the various revisions of the code. The Indian Standards IS 1893 code was first published in 1962, titled as Recommendations for Earthquake Resistant Design of Structures. So the first code was published in 1962 on 19th October. Then after that, the first revision takes place in 1966 in on August 7th. Then after that, the second revision takes place in 1970, third revision takes place in 1975, fourth revision takes place in 1984. Then after 1984, there is a fifth revision takes place in 2002. Then next revision 2016. Then seventh revision is in 2025. Now for 2002, 16 and 25, so the ACT 93 has divided into parts: part 1, part 2, part 3, like that. Now what are the various parts that we will see in the subsequent slides? So if you refer the IS 1893 2016 and 1893 2025, so the parts are as follows. In 2016 version of the code, there were only 5 parts, but now in the latest code, uh, there are 11 parts, including tunnels and coastal structures, steel towers. So these things were not there in the earlier code. So, part one is for general provisions, part two is for liquid retaining structures, part three is for bridges and retaining walls, part four for industrial structures, part five for base isolation buildings. And coming to the 2025 code, the part one is for general provisions, part two is on liquid retaining structures, part three bridges, part four industrial structures, part five buildings, part six base isolation buildings, part seven long distance pipelines, part eight steel towers, part nine coastal structures, part 10 tunnels, and part 11 earthen embankments. So these are the 11 parts that are given in latest version of the code. Now we'll see the equivalent static method. So the design earthquake horizontal force VBDH at the base of the structure, and the design earthquake vertical force VBDV at the base of the structure, considering the PSC spectrum, shall be estimated using the equation. Now you see the equation, that is VBDH is equal to AH into W. So in the 2016 version of the code, we consider VB VB is equal to AH into W, where AH is equal to the seismic coefficient. So here also the same thing, but the AHD is equal to Z into I into ANH of TH divided by R into W. Uh, and coming to the vertical direction, same equation, but whereas in vertical direction, the R value is taken as 1, because you don't have any inelastic in nature in the vertical direction of beams and columns. So that's why this R value is considered as a 1. And now we'll see each one of the parameters to calculate the earthquake forces using the latest code. So the earthquake zone factors is the first parameter, and the value of the peak ground acceleration divided by the acceleration due to gravity to be considered towards the estimation of the effects of design earthquake shaking on the structure, corresponding to the return period and earthquake zone in which the structure is located. So in the day one lecture on revision of the seismic hazard assessment by Professor STG Raghukant has detailedly explained what is the return period and earthquake zonation, how it is, how this zonation map has generated, and what are the various return periods, and all these details yeah, he was discussed. And coming to this, the zonation, the each and every return periods, the zone factor values are given. Now if you refer 2016 version of the code, we have only we have only four zones: zone 2, zone 3, zone 4, and zone 5. And the zone factor values are 0.1, 0.16, 0.24, and 0.36 g. But whereas here the same we cannot apply, because we have written periods. For each and every written period, the values are changing. Now, if you see for a structure, for a normal structure, the return period is 475 years. So, for 475 years, the maximum uh, zone factor was 0.5 g. But whereas in 2475 years, the zone factor value is 0.75 z. Okay, so now you have to take care for which kind of structures we have to consider the zone factor values. So as I discussed the building categories, so there are four building categories that we see in the next slide. So before going to that, what is return period? So the return period or the recurrence interval of the earthquake is the estimated average time between events of the specific intensity or magnitude occurring at the given location. Now let us take a simple example. What is the return period of an earthquake that has 2% probability of exceedance in 50 years? So we take the equation, that is Pn is equal to 1 minus of 1 minus 1 by t into whole to the power of n. Okay, so now from this equation, so this is what is the probability, that is the 2% probability. So 2% means 0.02, and n is the 50 years. So for this 50 years, you substitute here and calculate t. So where t is equal to 2475 years we get. So the same value you see here, this is 2% probability, that is 2475%. So like that, we take 2%, 5%, 10%, like that. Then the written period of the structures using by working stress method and limit state method. So these are the various types of the structures, that is the normal structure, important structures, critical structures, and special structures. So if I refer a 2016 version of the code, so the importance factor was different values for different cases. For normal buildings, the value was 1, and for important buildings like school buildings, hospital buildings, that kind of thing, the value was 1.2, and very very important structures, the value was 1.5. But here in this 2025 code, so the buildings itself, it is categorized, or the structures itself categorized as normal structures, important structures, critical structures, and special structures. For each one of the structures, the return periods are given. For normal structures, the return period is 175 years. For important structures, 275 years. For critical structures, 495 years. For special structures, 975 years for working stress method. But whereas in case of limit state method, the values are higher, a little bit higher values. For normal structures, the return period is 475 years. For important structures, the return period is 975. For critical structures, the return period is 2475. For special structures, the return period is 4975 years. And for each one of the category, what are the various uh, structures that come under normal structures? So a tabular column is given in IS 1893 part 1 of 2025, where you can see the what are the buildings that come, what are the structures that comes under each one of the category. For normal structures, for important structures, for critical structures, for special structures. So based on that one, you have to select the type of the structure and corresponding the return period. So for 2025 code, the importance factor is taken as 1 for all types of structures, because we have already accounted the return period, and for these return periods, the zone factor was different. You can see the zone factor values were different. Okay, so earlier the code, the zone factors are same for any kind of structure, but the importance factor changes. So the importance factor is to be used in the estimation of the design acceleration coefficient of the structure shall be taken as specified in the respective part of IS 1893 depending on the type of the structure. So for normal structures, important structures, critical structures and special structures, the importance factor is taken as 1. So this is given in clause 8.2.2 of part 5 of IS 1893. And coming to the design spectrum, which is very important, the in the day one session, Professor Ravikant explained about formation of the design spectrum, how many acceleration data that we have to consider to formulate this uh, design spectrum to meet the international standards. So here the design spectrum for equivalent static analysis is the diagram which I have shown here. The figure that I have shown here is only for the equivalent static analysis method. Similarly, for dynamic analysis, you have another spectrum, and you can see clause 6.2.3.2 of part 1 of IS 1893. So here I am representing only the equivalent static analysis method design spectrum. And here there are two cases, if the structure is located above the ground and if the structure is located below the ground. And for the structure, if the damping ratio is 5% and if the damping ratio is other than 5%. So for these cases, how we consider the design spectrum? That is NH of 5% of TH. So how do we consider these values? So as we know that there are various site classes A and B, C and D. So this we will discuss in detail after the design spectrum part is completed. So for site class A and B, for the periods, fundamental natural periods is in between 0 to 0.4 second, then the value is taken as 2.5. Now you see in the diagram, so the value is, the maximum value is 2.5 second for site class A and B, C and D, the value is taken as 2.5, but the maximum TH values are different. For site class A and B, the TH value is maximum value is 0.4. For class C, TH value is 0.6. For class D, the maximum value is 0.8. So this you can clearly see in the diagram. So the maximum value is 2.5 and 0.4 for site class A and B, so which is represented in green color, and the blue color is represented site class C. The value is 0.6, and the site class D is represented in red color, and the value is 0.8. Similarly, if the value is in between 0.4 to 0.6, so 0.4 to 0.6, so where the decrease in design spectrum takes place. So if that is the case, then what is the equation to be used? So for that, whatever the TH value that you calculated, just you take the inverse of that for site class A and B. But whereas for class C, the value is taken as 1.5 times 1.5 divided by TH. Similarly, for site class D, it is taken as 2 divided by TH. Now, in the earlier version of the code, that is 2016, so the spectrum was 4 seconds, but here in this case it is extended to 10 seconds. Okay, so because we account for the um, high-rise structures also. So for that case, if the time period, that is TH value, is in between 6 to 10, then you have to consider 6 divided by TH square for site class A and B. For site class C, the value is taken as 9 divided by TH square, and for site class D, the value is taken as 12 divided by TH square. So this is how we consider the uh, design spectrum value, that is ANH for 5% of TH value if the building is located above the ground. Similarly, in vertical direction, in case of vertical direction, the factor values you have to multiply with delta VTV. So what is delta VTV? So for that also the equations are given for site class A and B, site class C, site class D. Okay, so if the value is in between 0 to 0.01, then directly you have to consider 0.8 for site class C and B. For site class C, 0.82. For site class D, 0.85 you can take. And for the other values, if the value is in between 0.01 to 0.1, the value is zero point 0.8 minus 1.48 into TV minus 0.1. So the value, the TV value you have to substitute here and get the delta V value. That value you have to multiply with the these values to obtain ANV for 5% of TV. Then the normalized horizontal and vertical PH values, whatever we discussed here, are the acceleration values. Now to obtain the velocity values and the displacement values, so you have to multiply with velocity, you have to multiply with th divided by 2 pi. For displacement, you take the square of th divided by 2 pi. Then, for below ground structures, for the structure or the portion of the structures buried below the ground by the drilled in place construction method, the normalized horizontal and vertical below ground shall be estimated as the equation which is given here. That is A N H B for 5% of TH, which is if the like depth from the ground is in between 0 to 30 meters, then you use this equation, that is 1 minus he divided by 60 multiply with ANH for 5%. So whatever the ANH value that you calculated previously, that you multiply with 1 minus he divided by 60. Suppose if the depth is say 15 meters, okay, from the ground level, so 15 divided by 60, so whatever the value that we get, so that multiply with ANH to obtain ANHB. So B represents the below ground. Similarly, if the value is more than 30 meters, then simply we take 0.5%, sorry, 0.5 times of ANH value. Similarly, for vertical direction also. Then, in the drilled in place method of the construction, so this reduction shall be considered in the earthquake analysis of such structures only by the equivalent static method. So it is applicable only for the equivalent stat. Whatever the equations that I showed here, it is for equivalent static method and not by the response spectrum method. For response spectrum method, we have another equations. Okay, so this reduction shall not be considered in the cut and fill method. So cut and fill method means just we dig the soil and we fill somewhere else. So for that kind of construction, so this is not applicable. Okay. So these reductions A, NH, B for 5% of H and vertical direction shall be used only for the estimating inertia effects due to the masses buried at the corresponding levels below the ground. The inertia effects for the above ground portion of the building shall be estimated based on the unreduced ANH of T and ANH of P. So if we construct a tall building and for some floors, maybe three floors or two floors are below the ground, then we have to consider the below the ground portion ANH of ANHB value, and for the above ground you have to consider the ANH value. And the normalized horizontal and vertical, similarly similar to the earlier case, above ground case, we calculate the velocity as well as the displacement values by multiplying with the th by 2t and th by 2t square, as we discussed in the above ground case. And if the structure has more than 5% of the critical damping, then what do we do? So if you see the 2016 version of the code, then the values are given for each one of the damping ratio value, but here the equations are given directly. Okay, so unless stated otherwise, the damping to be used in estimating the design earthquake load shall be taken as 5% of the critical damping in exceptional cases like sloshing method, sloshing modes in liquid retaining structures, and special components of the industrial structures. Value of the damping other than 5% of the critical damping shall be considered. So for that, sloshing methods means water tank kind of structures, and industrial structures. So for these structures, the values are given in the respective codes. So in the beginning of the slides, I discussed about the what are the various parts of IS 1893. So in that industrial structures and water tanks, so these two are the parts. So in those parts, you have to take the equation if the damping ratio is more than 5%. Okay. So for those kind of structures, but for normal structures, we have to consider ANH of T is ANH for 5% of TH multiply with delta zeta value. So this delta zeta value is the factor to be multiplied with ANH of T to obtain ANH if it is greater than 5%. Okay, so this equation is the same. The ANH is the same calculation that I discussed, and this delta zeta value you have to take it into account. So for delta zeta value, you have a big equation. If the TH value is 0 to 0.1 and 0.01 to 0.1 and 0.1 to TAV and TAV to 6 seconds. So that means the TH value ranges from 0.01 to 6 seconds. Okay, so if it is more than 6 seconds, then we have to consider the one value, delta zeta value. So that means whatever the ANH value, so that is equal to ANH of T. Okay. Similarly, in vertical direction. So then the corner period, that is TAV. So this TAV is the corner period. So you can see what is that corner period. So these are the corner periods, that is 0.4 and 0.6 and 0.8. So these are the corner periods, which is represented with the symbol TAV. So we initially the value is 2.5, it's the constant value, and after that it decreases as the time period increases. So that junction value is considered as a TAV. Okay. So the corner period demarcating the junction of the acceleration sensitivity and velocity sensitivity regions in is taken as 0.4, 0.6 and 0.8 for site classes A and B, C and D respectively. So that values, if the zeta value is 0, then eta maximum value is taken as 3.2. If zeta value is in between 0 to 0.005, that is the 5% of damping, then we have to consider 3.2 minus 268 into zeta value. And if it is in between 0.0, that is 0.5% to 5%, then the equation is 7 divided by 2 plus 100 zeta whole to the power of 0.6. And if it is in between 0.05 to 0.3, that is the then we take 10 divided by 5 plus 100 zeta whole to the power of 0.5. So this eta maximum value after calculation, you substitute that value in these equations to obtain delta zeta value. Once delta zeta value is obtained, that delta zeta value you have to multiply with ANH value to obtain ANH of TH if it is more than 5%. So no expression is provided for n eta max zeta for values of zeta more than 30% of the critical damping. So now you see here the maximum value is 0.3, that is the 30%. So no equations are given in the code if it is more than 30%. When such cases, so if at all any case that arises, if the zeta value is more than 30%, okay, so then if that is the case, then you have to consider zeta is equal to 0.3. Next, coming to the site classes. So the site class of a structure shall be placed under one of the site classes presented in table below. Okay, so based on the weighted average VS of the individual values, VSI underlying soil strata I, where I belongs to 1 to NL, that NL is the number of soil layers. So now you see here the equation is given for calculating the Okay, that is a weighted average shear velocity value. So Vs is equal to sigma I is equal to 1 to L Ti divided by sigma I is equal to 1 to NL into Ti divided by Vsi value. So now here there is a strata which represents different soil layers, and for each soil layer the shear wave velocity values are given. So this is what is the profile of the shear wave velocity along the depth from 0 to 100 meters. Okay, so excuse me. So these values, the shear wave velocity values are here to obtain the weighted average Vs value, and that weighted average Vs value you have to be considered to distinguish the soil layer. So we have three types of soil layers: site class A and B, site class B, and site class A and B, site class C, site class D. So now for what are the various Vs values for all those categories? Now you can see here A for site class A, the shear wave velocity value is more than 1500 meter per second, and for B in between 760 to 1500. For site class C, it is in between 360 to 760. For D 180 to 360. For E it is less than 180 meter per second. Now based on that we have A and B site class, C and D. Now if weighted average Vs value is let us take say 800. So 800 which comes under 760 to 1500, so that comes under site class B. But the design spectrum is given for site class A and B, so that means you can take A and B category and proceed with the calculations. Now the shear wave velocity values, so if the data is available, if the data is not available, then the empirical equations are given for different types of soils based on the fc value. So this fc value is the fineness content value. So if the fineness content value is less than 15% for dry sands, and less than 15% for saturated sands and for clays, so these value empirical equations are to be used for obtaining the VSI values. Okay, so for sands, this expression for clays FC is greater than 15%, and these correlations are not applicable when N160 is less than 10. Detailed field investigations shall be employed. Next parameter is the approximate fundamental natural period. The approximate fundamental natural period in translational natural period T of the oscillation less than 50 meters in height shall be estimated by the following expressions. So if the TA value is 0.075 h to the power of 0.75 for RC, 0.085 h to the power of 0.75 for steel. This is for bare moment resisting frames with no infills. And for RC buildings, the value is 0.075 h to the power of 0.75 divided by a big equation is given. Okay, so which represents a lot of parameters. So if the values are available, then we can substitute it to obtain the equation. So where like rho cc and all these equation, all these parameters are available here. So rho cc and n csw is the number of concrete structural walls, and rho cc is the structural plant density of all concrete columns at the base of the building, and rho CSW structural plant density of the concrete structural wall, and LCSW is the length of the structural wall, concrete structural wall, and other parameters are given. So generally we consider for RC buildings TA is equal to 0.075 h divided by h to the power of 0.75, and for all other buildings TA is equal to 0.09 h divided by root d. So this is what is the normal equation that we use for calculating the approximate fundamental natural period of the building. But if this equation is applicable only for the buildings whose height is less than 15 meters, but if the building height is more than 50 meters, then you have to go for the IS 16700, that is 16700. This code is for high-rise buildings. Then elastic force reduction factor. So earlier it was response reduction factor. Now it is changed to elastic force reduction factor. So the force by which the base shear induced in a structure, if it were to remain elastic, is reduced to obtain the design base shear, which depends on mainly three parameters. One is ductility, second over strength, that is the partial factor of safety, and the third one is the redundancy. So this same uh, clause is taken from ICT 93 part 5, and the clause is 8.2.3, and the values, the R values for various uh, like frame based systems and wall based systems are given in table 7, and the entire values and the systems are shown in this picture. So this picture is also generated using AI tool. And the R values, if you see for frame based systems, special moment resisting frames offering high ductility, steel, either steel moment resisting frames or as well as RC moment resisting frames, the R value is taken as 5. And steel brace systems show a wide performance range. For ordinary frames and eccentric braces, the value is in between 3 to 5. And ordinary moment resisting frames have low ductility. For steel and RC, the R value is taken as 3. And for wall systems and dual systems, dual structural systems are rated for maximum ductility, then R value is taken as 5. For special RC structural walls provided excellent performance, then the R value is 5. And for unreinforced masonry, the R value is taken as 1.5 to 2.5. So these values, I already checked with the code in the and these values are perfectly all right, though the image is generated using AI. So this image is only to give the glance of the R values, because in tabular column it has two pages at tabular column, so it is very difficult to see and remember the values. So for that reason, I thought that to generate a kind of a image using AI tool and represent here for both frame based system as well as the wall based system. Then coming to this R, the definition of R is the product of ductility, overstrength, and redundancy. So now, what is ductility? Ductility is the ability of the structure to undergo the large deformation without significant loss in the strength. Okay, so that is represented by the letter mu. And overstrength is the high strength than assumed in design, provided the safety margin against collapse. So this is like a partial safety factor. And the redundancy is multiple load paths, reducing the impact of local failures. So this is represented redundancy. Now these three parameters are represented in the form of uh, a graph. It is the take the structure and apply the horizontal load, then calculate the elastic response and calculate the non-linear response or inelastic response. Okay, so the line straight line represents the linear elastic response, and the curve represents the non-linear response. Okay, so this is the maximum force if the structure remains elastic, which is represented by F, and the maximum load capacity, so that is in non-linear, so that is represented F5, and Fs is the that is the first yield point, and Fdcs represents the design force. Now this is ductility is in between Fei and Fi, and this is due to redundancy, that is in between Fi2 and Fs, and overstrength is due to in between Fs and Fdcs. Okay, so this is how the ductility, redundancy, and overstrength is calculated for calculating the R value. and this figure is taken from uh, taken by Professor CVR Murthy. And the loss parameter for calculating the VB value is the seismic weight. So the seismic weight of the structure is the sum of the seismic weights of all floats above the base of the structure is taken as the seismic weight of the structure. Now, what is the seismic weight for each and every floor? So it is given in clause 3.39 of IS 1893 part 1. For each and every floor, how do we calculate the seismic weight? So the sum of dead loads of the floors, appropriate contributions of the weights of the columns, walls, and any other permanent elements, including equipment vessels, tanks, hoppers, and containers from the stories above and below, finishes and services, and appropriate amounts of the specified imposed loads on the floors. So the same definition which is given in the earlier version of 1893 also. So in similar fashion, we calculate the seismic weight of floors and seismic weight of the structure. So then, after calculating the the seismic weight and ANH value, substitute in that equation to obtain VBDH uh, to obtain the shear, base shear value. Now, uh, whether the Bayesian value is correct or not, how do we find out? So for that, there is a limit, lower limit of the design horizontal Bayesian. So that is VBDH minimum is equal to 0.625 into ZI divided by R into W, which is less than or equal, which is greater than or equal to 0.015 W. So if this condition satisfies, then it achieves the minimum design horizontal base shear. Okay, so that is given in clause 3.39 of IS 1893 part 1 of 2025. Okay, and this is applicable only for the buildings whose height is less than 50 meters. So as I told you, if the building height is more than 50 meters, then we have to follow IS 16700. Then after obtaining the base shear value, then that base shear value you have to distribute onto the each and every story of the structure. So in the design excuse me, the design horizontal earthquake base shear force, that is VBDH, obtained shall be distributed along the height of the building and in plan at each floor level as specified hereunder. Distribution of the base shear forces as floors lateral forces at different floor levels is computed as. So similar equation is used in the earlier version also. So that is given in a clause 8.2.4.5 of IS 1893 part 5. So after obtaining the Q value, that is the uh, shear, each and every story, then that we have to distribute onto the vertical members. Now you see here in buildings whose floors can provide rigid horizontal diaphragm action in their own plane, that is VDIH, shall be distributed to the various vertical structural elements in portion to their lateral stiffness. So once the story shear is obtained, so that story shear is to be distributed on each and every frame. Okay, so excuse me. So that is based on the lateral stiffness. And in buildings whose floors are not capable of providing rigid horizontal diaphragm action in their own plane, VDIH shall be distributed to the various vertical structural elements in proportion to the masses from tributary floor areas. Or alternatively, then you have to model the flexible floor as a flexible diaphragm. So these are the two ways for that case. And VDIV shall be distributed to all vertical structural elements, including those that are not part of the lateral load resisting systems, in proportion to their axial stiffness. So these three clauses are given in Part 5 of IS 1893, and the clause is 8.2.4.5. So this is how we calculate the earthquake forces and apply onto the structure. This is related to only the equivalent static analysis. And the presentation is dedicated to the professionals and researchers contributing to the refinement and interpretation and implementation of IS 1893/2025 for improved seismic safety of Indian built environment.